Practice though. Everybody want to say hi, Miss Homan's class. So 1, 2, 3.
Hi, Miss Homan's class.
You guys are pathetic. All right, that was sad. That was really weak. They're gonna wonder. Mr. Hazelworth's class must be really boring. All right. So that said, though, we are going to begin chapter 3. Today we're going to talk about exponential functions and their graphs. Okay. Now, talking to Mr. Griebel this morning, Ms. Hermson this morning, so you may have had one of those two in Honors Algebra 2. Sounds like this is something that you covered in pretty good detail back in Honors Algebra 2. So we need to pull that information out, the recesses of our mind, and bring it forward here. Right? So to start out, we want to kind of give you an introduction to what an exponential function is. Okay? Now, we have to differentiate between an exponential function and just a polynomial function. Okay? When we say exponential function, what we mean is that the variable is in the exponent. Okay? And that's what we see here in our general function. We have f of x is equal to a to the x power. That's what makes this exponential. So let's write some things down here. And we'll point out some important pieces. All right, so let's talk through a few important things here. The first thing that I want to talk about is that first bullet point, why A has to be these certain things that are listed out there. All right, so A is representing the base of that exponential function. Okay, probably a term that you've heard before. Now, let's start off by thinking about why A would have to be greater than 0, which makes it positive. All right, what do you know about negative numbers as we change the exponent of negative numbers? It switches back and forth from positive to negative, right? So let's say that A was a -1, right? And -1 to the first power is -1. -1 to the second power is 1. -1 to the third power is -1. It bounces back and forth, okay? So that's why our base always has to be a positive number when we talk exponential, okay? The other thing is that A cannot be 1. Why do you think A can't be 1? Just be a constant, wouldn't it? I mean, if you take 1 and raise it to any power, what is it? 1. It doesn't change it. All right? So when we talk about the base, those are the reasons why we say the base has to be positive and it can't be 1. All right? We need to get this exponential function to show up in the graph. Okay? Now again, we might look at this and say, well, f of x down here has an exponent, right? But again, the difference between this function and our exponential function is the position of the variable, right? Where is the variable at? That's what makes it exponential, okay? So let's remind you about some important characteristics of an exponential graph and what the parent function would look like. So here's the two graphs that can occur when we deal with an exponential function, right? And we've got some important information here with regards to the domain, the range. We're given the y-intercept, where the asymptotes are. So I'll let you jot that information down, and we'll talk a little bit about these graphs. you guys think I should put some subliminal messages in these videos? Like if while you guys are writing notes, I just stood over here and whispered, "You love to graph, you love to graph." Subliminal messages.
I kind of forgot you were recording.
From now on, whenever you ask a question, you're going to have to start out with an introduction of yourself. Hello, my name is Mr. Hazelhorse. I would like to know, and then you can ask your question. All right, so let's go through some information here about each of the graphs. Now let's start out with the two different names that we would categorize each of these two graphs under. So again, think back to your Algebra 2 days. If we have an exponential function that is increasing as we move from left to right, does anybody remember what we call that type of exponential graph? Exponential starts with a G, ends in a row. Growth, all right? So remember that name, that term, exponential growth? All right, that's what we see in this example, right? So this is a problem of exponential growth. Now I'm going to hope somebody can figure out the other one then. All right, so the graph goes down. That's right, it's an exponential decay. What's the difference between an exponential growth and an exponential decay? Right. Values become smaller. What causes them to become smaller? The negative exponent. That's right. When I look at my exponential decay, it's a to the negative x power. All right. Exponential growth is a to a positive x. Now, if we remember our transformations, we should recognize transformation-wise what's happening to the graph. If I make my x value negative in any graph, what does that do to the graph with regards to transformation? That reflects on the y-axis, and that's what we see here. Right? These graphs are a reflection of each other about that y-axis. Okay, so we want to remember those transformations when we go back to chapter 1. All right? Now, notice they both have the same domain and range. Okay? And those domains and ranges, since we don't have any vertical asymptotes, are going to extend forever horizontally. That's why our domain will always be a negative infinity to a positive infinity. Our range will be impacted by whatever our horizontal axis is in both functions. Okay? And the parent function, if we just have the basic exponential function, and it doesn't matter what the base is, right? A could be any number. Right? Because if I take A, and A is any number, and I raise it to the 0 power, what's anything to the 0 power? It's 1. Anything to the 0 power is 1. All right? And that's why our intercept is always the point 0, 1. All right? Because again, anything to the 0 power is always 1. So these are some important characteristics about the exponential graph that I expect you to know. We should be able to come up with those pretty quickly. Okay? And if we understand some basics about the graph, those are pretty easy to come up with. Okay? All right, questions on those parent functions at all at this point? All right, so let's talk a little bit more about transformations then. Those are going to be important as we think about graphing an exponential function. If we know the parent function, right, we should be able to apply some different transformations. Okay? Now, I wouldn't write all these down if I were you. We just want to review the transformations. Okay? So let's look at a couple of equations here. Let's start at the top left here. So our parent function for all four of these graphs is f of x is equal to 3 to the x power. Okay? So you'll notice that's a function of all four graphs. Okay? So now let's describe what was the transformation that happened to g. So look at that function. It's 3 to the x plus 1 power. X plus 1 is all the exponent. Okay? Now think about what you already know about transformations. Right? What's happening to this graph? It's moving which direction? To the left. How many units? 1, right? Because remember, if I plug a number in with x, right, that creates a horizontal shift. It's either shifting left or it's shifting right. Okay? And remember, x is always kind of our liar. The sign is always actually opposite when it moves. So when I look at this one, this graph has been shifted left 1 unit. Again, as we apply that transformation. Okay? So let's skip to the top right. Right, again, we have the same parent function, f of x equals 3 to the x. Right, let's look at this transformation. Okay, what's happening here? Down 2, right? So this function, right, shifted down 2 units. Now, I want you to think about, if I shift it down, right, what are some things that are going to be impacted by a shift down on that graph? My asymptote change, right? Normally in the parent function, the asymptote is the x-axis. But if my whole function gets shifted down 2 units, my asymptote gets shifted down 2 units as well. Right? So the asymptote of this function would be y equals a -2. Because it's shifting down just like the graph. Right? What else would shift down here? What else do you notice shifting? Our intercept, right? Our intercept is normally at the point 0, 1, but notice if I shift it down, it also shifts down 2 units. Okay? So this is where if we have a knowledge of those key characteristics of the parent function, we can apply those transformations to see how those things will be impacted as well. Okay? So those are some important things that we want to pick up. Okay? Now, if we look at the bottom graphs, these are both just representing reflections. Okay? Now, you might look at this problem and say, I thought you said we couldn't have a negative base. Right? And I would tell you the base is not negative. And if I wanted to write a negative base involving exponents, what would I have to include in that problem? Some parentheses, right? If I wanted to write a negative base, I'd have to write k of x is equal to, in parentheses, a -3x. That's a negative base. Okay? In this problem, the base is still 3, right? The negative sign is not being impacted by the exponent, right? We raise 3 to whatever power we need to, and then we reflect it, right? We make it negative. So that's what causes this reflection about the y-axis, right? And a reflection in the x-axis, a reflection on the y-axis, again, that's where we change that variable and make it negative. That's the difference between exponential growth and exponential decay. Okay? So as we think about graphing these exponential functions, we want to start out with just being able to identify those transformations. The same thing that we did in chapter 1. Okay? Can everybody see how we visualize those transformations as we look at those in the graph? So again, we look at the top left. The shift is up with x. Right? Here the shift is on the function. And then we can see where those negative signs go to get our reflections. Okay? Questions on that one at all? All right. So before we can get into some other problems, let's describe some transformations by looking at the function. Right? So here we don't have the graphs. So let's just see if we can take these functions. And here's our parent function, 4 to the x power. All right? So we're going to describe the transformations, and then we're actually going to sketch a graph of the function as well. Okay? So let's take 4 to the x minus 2 power. What transformations do we have there?
Right.
Just a shift right 2, right? Okay? Now, if I sketch the parent function of this, all right, let's start out with the parent function. We'll put that in red. So if I just sketch the graph of 4 to the x power, okay? Again, I just need a sketch of it. I don't expect something perfectly accurate, right? But there's some things that we should know about that function. Is this growth or decay? It's growth, right? It's going to be going up, okay? Where's it going to cross the y-axis at? At the point 0, 1, right? That intercept never changes unless I shift it. We're just graphing the parent function here. So we intersect at 0, 1. Where would our horizontal asymptote be? X-axis, right? So this would be the graph of my parent function. I'm just going to draw it as an exponential growth. Okay? So now, if I take that graph to draw the new function, let's put that in blue. All right, how should the graph in blue compare to what we see in red here? Just shift it right 2 units, right? So if I just shift it right 2 units, right, this point is going to end up over here now. Right, I'm going to move that y-intercept over 2 points, right? And I'm just going to follow the same pattern. It still has the same asymptote. I'm just shifted over 2 units. Okay? Again, I don't expect you to take the time to plot a table of values and get all these points perfect. Right? I just want you to quickly be able to analyze the function and sketch a graph of it when we compare it to the parent. Okay? So again, our graph in red is our parent function. Our graph in blue is that g of x. Okay? Questions on that one at all? All right, how about our next one? What are our transformations there? Right. So reflect on the y-axis. And up 3, right? Okay, so let's sketch a graph of that one. Now, I'm not going to draw the parent function this time because it'd be the same parent function as our first one, right? So if we took that point, right, the y-intercept, that point is going to shift up 3 units, right? So if we go up 3, we're at 4. Where would our horizontal asymptote be in this problem? Up 3 units also, right? From the x-axis, our horizontal asymptote is now here. And we need to get the reflection in, so we're going to draw this one as a decay. Right, so this graph should just go downward in an exponential pattern. So we have the reflection about the y-axis. That's what makes it a decay. And we have the horizontal asymptote and the intercept shifted up 3 units. And that gives me enough information to just rough sketch that graph. Okay? So that'll be something that we need to have the ability to do is, can you just sketch a graph of the function? Okay? And again, I don't expect a ton of detail. I just want to see your knowledge of the transformations applied to the parent function there. Okay? Questions there at all? All right. So next up, let's talk a little bit about an important number when we talk exponential functions. And we need to remind you a little bit about the natural number. Okay? So E is an important number when it comes to exponential functions. Right? E is kind of like the number pi. It's irrational. So it's this infinite non-repeating decimal. And that's why we use the letter E. It's like the pi symbol has its own symbol. Or the pi number has its own number. So it's approximately 2.718281. Right, again, that would be this infinite non-repeating decimal. But this has a lot of applications in exponential settings. Now, if you have your calculators handy, go ahead and pull those out. And I'm going to pull up my graphing calculator as well. And we want to point out where the natural number is on our graphing calculator. Now, if you read the first slide, a lot of the tests and quizzes we've taken to this point in the year have been non-calculated. Okay? This chapter, you get your calculator back when it comes to tests and quizzes. Okay? There will still be times where we'll bounce back and forth. We'll have some tests or some quizzes where it's part calculator, part non-calculator. All right? But we need to exercise the greatest calculator that you have available to you, and that's your mind. Okay? So there will be times where those calculators are off limits, but this chapter, you get them back. Okay? So when we look towards the exponential number, it's pretty easy to find. If you look on the left side of your calculator, right next to basically the 4 button, you'll see your natural log button, ln. And right above that, we have e to the x power. So to access the exponential number, we just need to press our second button and then the natural log button. And that will bring up e. Okay? Now, some of you, if you have an older TI-83 calculator, it's going to come up and it's going to write e with a caret, and then you've probably got a parenthesis. Okay? So that parenthesis is saying this is what I want in my exponent. All right? So when you get done typing whatever you want in your exponent, so if I want to raise e to the 8th power, and then maybe I want to add 2 to that afterwards, I need to make sure that I close my parentheses. Now, some of you might have a newer model calculator like the one that I have up here, so it kind of puts a little exponent box up there. So if I wanted to take e to the 8th, and then I use my arrow key to get out of the exponent, and then I can add on anything from there. But we can see the difference between what's in the exponent and what's out of the exponent. Okay? So you need to make sure that you're comfortable with your calculator and how to use that effectively. Okay? So that's the E button. Now, the reason why we want to show you where that is because we want to remind you of some compound interest formulas. Do you remember working with these in Algebra 2? All right. So these are coming back as well. These are an important application of exponential functions. So we have 2 different compound interest formulas. And how you determine which one to use is based on how your interest is being compounded. We'll let you write down those formulas and jot down some notes about the variables. We'll look at a couple of examples and practice with your calculators here as well. Now, interest is one of those concepts in mathematics that will impact you all at some point in your life. This is something that's important to know. Right? But do you know why banks pay interest if you put money in an account? That's true. They give you a motive to give you their money, because guess what they're going to do with your money?
Invest it in themselves.
They might invest in themselves, or they loan it to somebody else. So a bank, when they give you interest, they're basically paying you money to let them use your money. Now, they're also smart. If you know anything about interest, right? They charge way more interest than they give out, right? So, like, if we put money in a bank account, you put money in a savings account, you're lucky to get like 3% interest in a year. But if you take out a loan from the bank, you're probably going to get charged 5, 6, 7%, right? Maybe more than that, depending on the type of loan. So banks are smart. They're a business. They need to make money. So they make more than they charge or than they give out. And but that's the whole idea of interest, okay? And in a way for us, if we put money in an account that gains interest, that's just like getting free money. Right? Your money is working for you. It gains interest as it goes. Now let's see if you remember anything from Algebra 2. Do you remember what type of compounding is better? A certain number of compounds per year, or if we compound continuously? Continuously, right? And that should make sense, right? If it's compounding continuously, it's constantly making money, okay? But if I only compound a certain number of times a year, some banks, they might compound monthly or quarterly. If I compound quarterly, it's only making money on 4 days a year at the end of each quarter, okay? So that interest doesn't grow as fast in those types of compoundings, okay? Now, a couple of things that we need to point out in this formula. All right, we need to make sure everybody understands what a principal is. Okay, the principal is the amount of money that you begin with. How much are you depositing? That's your principal amount. That's where we start. All right, for our compoundings per year formula, N is representing how many times will it compound. Now, let's talk about a couple of different words. Okay, quarterly compounds 4 times. Right? If we compound annually, how many times is that? Once. Semi-annually? Twice, right? Quarterly is a popular one. Weekly, how many weeks are in a year? 52, right? Those are all important terms to just be aware of. Right? For both formulas, when we input rate, and I didn't put the decimal underneath the continuous compound one, but rates always have to be inputted in terms of a decimal. Right? They'll be given as a percent, but we need to make sure we shift that decimal point over. And then finally, time. Generally, it's going to be talking about a year. How many years is it? Sometimes it'll be a month. Okay? But those are our times. So those are our formulas. A lot of times people call this the PERT formula. It's kind of an easy way to remember it. Right? That's involving that exponential number, that natural number e. Okay? So let's put these formulas to work. We'll utilize our calculators to help us out here. Let's take a look at the compound interest formula. Okay? So here's our first problem. All right, we'll do it using both formulas here. So we've got $12,000 that we're going to invest. We get an annual interest rate of 9%. That's pretty solid. You can get a bank to give you 9%. Go with it. And we want to find the balance after 5 years. And we're going to look at 2 different types of compounding. So we'll start off quarterly, and then we'll also look at it being compounded continuously. Okay. All right. So let's start out with the first formula, since we're compounding quarterly here. So if we set up that formula, our amount is going to be equal to, first thing we need is our principal. What's our principal in this problem? 12,000. Then we're going to set up a parenthesis. Okay. And we've got 1 plus. And now we need R over N. What's our R in this problem? 0.09, right? We always want to input that rate as a decimal, so 0.09. And then remember, N is representing how many times it's going to compound, which would be what in this problem? 4, since we're compounding quarterly. And now we need to raise this to the N times T power. So N is 4 again. What's our T in this problem? 5. Now, let me pull up my calculator, and let's show you how we can type this all in at one time. So, grab this here. Let's switch it to the other side of the screen. We'll slide over here. All right, so let's type that formula in. So, basically, we're going to type in exactly what we see. I'm going to type in 12,000. I'm going to hit a parenthesis. Your parenthesis buttons are up above the 8 and 9. So we'll go 1 plus 0.09 divided by 4. Now your calculator is programmed to follow order of operations. And that's important for us to keep in mind when we type things in. That's why we need to include the parentheses here. So we need it to take 0.09 and divide it by 4 and then add the 1. It will do that the way that we have it typed up because we know division comes before addition in order of operations. Now, to raise to a power, if you look over on the right side of your calculator above the division button, you have this caret key. So if you hit that caret key, that represents an exponent. Okay? So now I can just type in 4 times 5, or we could do the actual math ourselves and type 20. We'll hit enter. And there's how much money we'll make at 9% interest after 5 years. What did I type in wrong? Let me see what you do wrong. Oh, you got 1 too many parentheses. You don't want that parenthesis in between before the 0.09. Because otherwise, there we go. All right, you get that parenthesis in beforehand, it changes the order of things. Okay, you don't need that. Back to 2 years worth. You got 4 minus 5 and 6 times 5. Yeah, you just got that wrong. So I changed it so we got it. There you go. You good? Make sure. When you put that caret key on your typing calculator, we need to put a parenthesis after that. Otherwise, it only raises it to the 4th power, and then it multiplies to 1.5. So whenever you get that caret key, put a parenthesis. Okay. Anybody else have issues with their calculator? We got the same thing? All right, so let's compound it continuously then. All right? So if we compound continuously, here we're using our PERT formula. So again, our principal amount is 12,000. We're going to raise this to E, or multiply this by E, and then our exponent would be the rate times the time. So 0.09 times 5. And again, we can just input that right into our calculator. So if we type in 12,000, and then we use our natural number button. Now again, at this point, the natural button number, we're applying an exponent here, and we want all the rest of our number to be in that exponent, or the rest of our formula. So we'll go 0.09 times 5. Come on. Okay? Yep.
Would doing like the second and then the E and then the caret, would that be like the same thing?
Yeah, we don't need the extra caret in there. Because your calculator, it either looks like mine where it kind of lifts that number up,
Yeah.
or it'll look like this where it will automatically put the caret there for you. Okay? So we don't need to put an extra
What I'm
caret in
saying
there.
is like what I did is I said second and then the E with the division button.
Yep.
And then I did the caret. So then it's fine. That'd be like the same
Good.
thing.
You're good. Good. All right. So if we go ahead and hit enter, now we know that we should make some more money here because it's compounding continuously. We can see that we do make almost $100 extra from that compound interest continuous. Okay? Now the key throughout this chapter, you're going to have the ability to use your graphing calculator, but that's not a very good resource if you don't understand how to use it. So make sure we get practice with that as we go. Make sure you know how to type things in. We can follow order of operations correctly. And that's going to be important as we go. Okay? Questions on that at all? Yes, ma'am. Yep, missing a 0. Now I'm going to show you guys a little shortcut. Sometimes you make mistakes typing something in, and if you don't want to type the whole thing in over again, if you hit second and then your enter button, it copies down the previous command. So like if you got an extra 0 in, I can just scroll back and I can edit that equation. Now, sometimes that'll be helpful if you don't want to have to type everything in over and over and over again. So that's just kind of a neat little shortcut to be aware of. All right, homework assignment today, though. Again, I got a little note reminding you to use your calculator here. All right, let's get rid of the rest of the people. Everybody have a great day. Use your brain.